In this session, we're going to discuss a new probability distribution variable called hypergeometric distribution variable. And this kind of variable deal with type of quality issues, for instance, acceptance sampling. Let's look at problem context. Usually we will looking at a batch of product. Say we have n objects. Out of these n objects, k objects was classified as success. The rest of n minus k objects classified as failure. And out of this total of capital N objects, we call it a batch of objects. We're going to take a sample of size n, lowercase n objects, randomly without replacement. This is very important, without replacement. Then we're going to have a sample with total number of objects of lowercase n, and our random variable defined here, x, denotes the number of success in the sample with sample size of lowercase n. Well, the variable here we defined is a hypergeometric random variable with probability density function equal to this function. F of x is equal to the combination of selecting x number of success out of total k success in the batch, multiplied by the combination of selecting n minus x number of failure out of total of n minus k number of failure inside the batch, then divided by the total number of possibility of selecting n lowercase n objects out of total of capital N objects in the batch. So if you recall that in the first exam we have a problem that asking you for the probability of selecting certain number of defective items. So what's the probability? This is exactly the formula to generalized formula for any x that's possible. X has to be less or equal to k number of objects that are possible in the whole batch. So this is called hypergeometric distribution. You can see that the distribution mass function is defined as a probability mass function, involves computation of 3 combinations. And the other thing that I want to mention is that if I slightly change the problem statement, instead of saying that the sample was selected randomly without replacement, we take the without out, say it's selected with replacement, then the problem is changed from hypergeometric to binomial. Because if you have sampling with replacement, then each one of them, each object that's been sampled can be considered as a Bernoulli trial with the same probability of success for each trial, and the success rate is capital K divided by n, because out of total number of n objects we have k success. Therefore each time you pick one, the chance of getting a success is k divided by n. So that's the p for the binomial, and the n is lowercase n is for the binomial distribution if you pick size n, and you want to figure out of this lowercase n how many number of objects are success. So let's look at one specific example. A batch of product contains 100 parts from supply A and 200 parts from supply B, and if 4 parts are selected randomly without replacement, what is the probability that they are all from supply A? So based on the problem statement, we define the success as the part was coming from supply A. Therefore, the whole batch contains 300 of total parts, and out of 300, 100 of them are success, 200 of them are failure. So here capital N is equal to 300, K is equal to 100, and we are picking 4 parts without replacement. This 4 is the lowercase n, and we are looking for what's the probability that they are all from supply A. So if I translate it to problem statement, then we define the variable x equal number of parts in the sample from supply A. So the x is number of parts in the total of 4 parts that are from supply A. So from the supply A, so there's a lot of possibility out there. You can have no parts from supply A. You have 1, 2, 3, 4, and the question is asking for all 4 of them. What's the probability all 4 of them are from supply A? So we are looking for probability x equal to 4, and we simply just need to plug in the numbers into the formula. C is k x, and C m minus k, this is m minus x, x is 4 and n is 4, so 4 minus 4 is 0, and here is the total number of objects, and capital N is equal to 300. Select 4 out of 300. This 4 is the lowercase n. So you just need to plug in the corresponding numbers. You get the probability mass function that in this example we just simply apply the probability mass function to solve the problem. And this problem can also be solved using Excel. You can easily calculate the number by simply typing a function, built-in function in the Excel called Hypergeometric Distribution. So let's do it here. So x, you want to find the number, you just type in x equal to h y p g e o m d i s t. That's a function, built-in function, and this function needs 4 parameters. The first parameter is the number of sample s, means the success number of success in the sample. Here we have, it's basically the x equal to 4, and the second parameter is number of samples that are success inside the whole population. So we have 100 success within the sample. Here the third number is the sample population. Sorry, it's a typo here, so I'm showing the right formula here. So it's the function is Hypergeometric distribution, and the parameters inside the parentheses are x, lowercase x, the number of success within the sample that are of interest, then followed by the sample size, lowercase n, then followed by the number success within the population, k, and finally the population size. So let's show it to you. It's x equal to Hypergeometric DSP. So you can see the first parameter is number of success in the sample, 4. Second parameter is number of objects in the sample is 4, is lowercase n. Population S is number of success inside the population, so it's 100. Finally, the final parameter is number of objects in the population, which is total number of capital N, 300. So if you calculate that, you will get the solution, get exactly the same number here. Let's move on, make the question a little more challenging. So the question is, what's the probability that 2 or more parts are from supply A? To answer that, we simply just replace equal to 4 to 2 or more. 2 or more means greater or equal to 2. Number of parts are from supply A, so we're still looking for the same number of success, x greater or equal to 2, the probability. And for x greater or equal to 2, since the total number of sample is 4, therefore the maximum number of success that's possible are 4. So probability x greater or equal to 2 is equivalent to find out the probability x equal to 2 plus x equal to 3 plus x equal to 4, and plug in this 2, 3, 4, replace it with lowercase x, and put into the formula. You see 100, select 2 out of 100 and select 4 minus 2 equal to 2 out of 200 divided by select 4 out of 300 plus select 3 out of 100 and the rest of 1 out of 200, still divided by select 4 out of 300, and lastly the probability x equal to 4 is select 4 out of 100 multiplied by select nothing out of 200 divided by select 4 out of 300. So finally we get the probability equal to 0.408. So you can get the same solution by plugging in the numbers. Sorry, this is also a typo. I copied from the textbook, and it end up actually there's some typo here. So you should switch the sequence of 4 and 100. So the second parameter is the lowercase n, and the third parameter is capital K. Finally, what's the probability that at least one part in the sample is from supply A? Here the keywords here is at least one part in the sample is from supply A. At least translate into math equation is greater or equal to. So to solve that, we're simply looking for probability x greater or equal to 1. and you certainly can do that by make that equal to x equal to 1 plus x equal to 2 plus probability x equal to 3 plus x probability of x equal to 4. You just add one more term from the previous question. But you can also do the same question using the complement. X greater or equal to 1, the complement is x equal to 0. And since x equal to 1, the probability plus the probability x greater or equal to 1, the summation is equal to 1. Therefore, this one is 1 minus the complements. And you can get the solution by doing this way. The hypergeometric distribution, let's look at the common characteristic for any hypergeometric distribution variable. If x is a hypergeometric random variable, and this random variable has to have three parameters: the size of the population, the number of success in the population, sample size, lowercase n. Then we have the mean or expected value is n multiplied by p, while the p is assuming if you are doing the sampling with replacement, then the p is simply the probability of random pick 1, what's the chance that one is a success, and this one obviously should be k divided by n, because you have k success in total of n objects. And this one seems to be, if look like it's the same. If you treat the problem as a binomial, you should have the same expected value. And the hypergeometric, actually later on we will see that the extreme case, while the lowercase n is a very small portion of the capital N, then you can have a fairly good approximation using binomial to approximate the hypergeometric distribution. And the variance for the hypergeometric distribution is also somewhat similar to binomial. You can see the first three terms in the equation, n multiplied by p multiplied by 1 minus p, is the variance of the binomial, equivalent binomial problem. And for hypergeometric, you need to multiply by a term, n minus lowercase n divided by n minus 1, and this one is a finite population correction factor. So you can imagine if the capital N is very large compared to the lowercase n, then this one will become the last term. This correction factor is very, very close to 1. So you can just treat hypergeometric and have almost the similar mean and variance as the corresponding binomial distribution. And the binomial is the one that you do the sampling with replacement. So each time you take one part, you check the parts to see if it's success or not, then you put it back into the batch and do the second sampling, and then you put it back after the second sampling, and so on and so forth. You keep doing that. That's called sampling with replacement. Then you have a problem of binomial distribution. Sigma square approach the binomial variance as the lowercase n divided by n becomes small. Let's look at another example. In this example, a list of customer accounts at a large company contains 1,000 customers, and out of this 1,000 customers, 700 has purchased at least one of the company's product in the last 3 months. So if any customer purchased at least one product from the company, we treat that customer as a success. So to evaluate a new product, 50 customers are sampled randomly from the list. So they just randomly draw 50 out of the total of 100 customer in the database, and the question is, what's the probability that more than 45 of the sample customers have purchased from the company in the last 3 months? So basically what we are looking for is you random pick 50 customers out of this 1,000 customers, and you want to check what's the likelihood, what's the probability that out of these 50 customers selected, 45 of them or more, 45 or more of them are from these 200 success customers. So since we are doing sampling without replacement, this is a hypergeometric distribution. And let's define X as the number of customers in the sample who has purchased from the company in the last 3 months. In other words, those customers are treated as success in the contest. And then the X is a hypergeometric random variable as with the following parameter. Well, capital N is equal to 1,000. That's a batch size out of the total pool of 1,000 customers, and this K, capital K, is 700 because out of this 1,000, 700 of them did purchase at least one from the company over the last 3 months, so we treat them as success. And the lowercase n is the sample size. The sample size is 50, and we are looking for the probability of the number of success greater than 45, more than 45. And since the total sample size is 50, so more than 45 means from 46 to 50. So you do the summation, replace the X with 46, 47, 48, 49, and 50. And do the summation, you will be able to get the solution. The problem is that this is a pretty lengthy problem. You will end up having 5 terms. Each one of them involved 3 combination calculation. So it's a lot of work. And fortunately, sometimes we can approximate hypergeometric with binomial. And what's good about binomial is that binomial distribution, a lot of software we have, or even statistical table, will provide you with cumulative distribution function, so you will be able to easily calculate the probability that involves greater or equal, greater or smaller than certain numbers. So for instance, in this particular case, probability X greater than 45 can be expressed as probability, this is the probability mass function for the binomial distribution, where the P is equal to 700 divided by 1,000 is 0.7. Success rate P is 0.7. But this seems still not significantly eliminate the amount of calculation. But wait a second, if you have Excel, access to Excel, you will be able to simply use a function binomial dist distribution, and this binomial distribution function have a parameter, the last parameter. So this binomial distribution function, the first parameter is X, which is in this case is 45, and the second parameter is the sample size N, and for this particular example, sample size is 50, and the P is the rate or the probability of success. In this problem, we have 700 divided by 1,000 equal to 0.7, and the last term, last parameter in this function is true or false function parameter, and if you state it as true, then this function calculates a cumulative distribution function. So You can see if I replace the cumulative parameter with true, what we are calculating is probability x less or equal to x. So it's, remember, the cumulative distribution function simply calculates the probability less or equal to the parameter. And if you assign a false value to the cumulative parameter, then this one is probability mass function. And for the problem in hand, what we are looking for is probability x greater than 45. Therefore, if we can somehow calculate the probability x less or equal to 45 and use 1 minus that probability, we will be able to calculate this one. So this probability is equivalent to equal to 1 minus probability x less or equal to 45, and the probability x or less or equal to 45, you can use this binomial distribution function in Excel to calculate that. Let me show you in Excel how we do that. So you just type in equal to 1 minus binomial distribution, and this distribution take values number of success, in this case is 45, and the number of trials, or its sample size n, is 50, and the probability of success is 0.7 because out of 1,700 of them are success. Lastly, we want true so that what we are calculating is the cumulative distribution function. Therefore, it will give us a probability x less or equal to 45 instead of x equal to 45. So if you change the true to fourth, then this part is calculating probability x equal to 45. So we will get the same value as in this table.